All right, so we're on page 750. I apologize, 749. And we're doing number 17. And so the question takes the coefficients and cuts the entire equation in half. Did you notice that? Like if you actually look at the coefficients in the equation on A, do you notice it cuts everything in half? Okay, so the fact that it cuts everything in half, you take the original equation and multiply everything by 1/2. That's what you're essentially doing. So as a result, your Q value, even though it currently is 6.5 times 10 to the second, you are now going to, Q prime is going to now be, take the coefficient and take the square root of it. So on your calculator, you need to be able to go ahead and, on the calculator there's a math button. Do you guys know about that? And on the math button, it actually allows you, if you press math, a screen will come up and you can scroll down and look for the square root symbol. And so literally this is really taking the square root of 6.5 times 10 to the second, and you will get 25. Let me know if you're getting that. Or you could do shift x squared. You could do shift x squared. Okay. Are you getting that? Yeah?
Yeah, I got it too.
Okay, cool. All right, so then our next problem would be number 23. So the way you have to work this is a multi-step problem, meaning you've got two equations. So the first one, and I'm just writing these down as given. So they give you those two equations, right? Right. So then your next step is you need to see how certain ones cancel out. So do you see how these two are going to cancel right here? Okay. Now before you do that, make sure these are balanced. So go ahead and balance each equation. What do you guys get?
Wouldn't the second one just be 1, 1, 1, because there's 3 F's and 1 0.
Mm-hmm. What about the top one?
1, 1, 2.
Okay, good. All right. Now what I want you to do is, you have to understand, this is a two-step reaction where these form this product, right? But this product automatically turns around and starts breaking down. It's called an intermediate when that happens. So in the end, you're not going to have any of this intermediate. So how we deal with that mathematically speaking is to get it to show that this is actually going to get used up anyways, you have to multiply this equation by 2. So double everything in this equation so as to keep the actual ratio. So all I did is I kept the equation, but I just doubled it, and my purpose was to cancel this. to cancel these two. Because when you're adding equations, things that are on the left and the right actually cancel out. So then you just bring everything else to the left of the arrow down, so you have Cl2 plus F plus 3F2, correct? So you bring your chlorine down, and then you bring your fluorines down. You have 3 of them. And then over on the right you have 2 ClF3. So we just added 2 equations together. And then there's a property that says when you can add 2 equations together, there's an actual formula that says you can also multiply their coefficients. So you might have a coefficient for this one, a constant rather, and you might have a different constant for this one. And there's a rule that says if you multiply these two together, you'll get the new overall constant for the reaction. So we're going to do that. We're going to take this equation right here, so we'll call this 1 and we'll call this 2, and we're going to write them as an equilibrium expression to get the final. So we're kind of doing a proof to show that when we multiply these two together, we get this one. So how do you show that? Alright, so you take this equation right here up top, number 1, it's going to look like this. Products over reactants, so it's going to be K equals F, CLF. So we're just using this whole thing right here before it all got canceled out here, before this got canceled. So we have CLF squared over Cl2 times F2, so it's going to be like this. And then we're going to do the bottom equation, equation number 2. So this is 1, and then K prime is now 2. So this is 2, equation number 2. We're going to put this over this. So it's the product, ClF3, raised to the second power because of the coefficient 2, divided by the product of these two chemicals raised to their powers of 2 because of their coefficients. So it'll look like this. We are trying to prove that if we multiply these two expressions together, we're going to get the expression for this one. So now what we do is we multiply these two together. So we can take this one. Oh, I'm not even going to try it. I'm just going to rewrite it. So we can take ClF. It's lagging. ClF. The expression from the first equation, multiply it by the expression from the second. What's going to happen is these two are going to cancel right here. Because anything, and then when you cross the dividing line, anything divided by itself is equal to what? 1, right? Because this goes into this once. So then what you have left is this in the numerator divided by the product of these 3 things. So simplified, it's going to look like this. And you're going to combine your fluorines because you have one here. F2 times F2 squared is what? F2 multiplied by itself 3 times is also written as cubed. That's right. Okay. And so then you can go back and verify, is this the expression for this final sum of these equations? Does this look like the expression for this? Yeah, and so we just proved that the product of the constants is equal to the constant for the overall reaction. Okay. And so literally if we had numbers, if they gave you numbers, K values for this one and this one, you could find the new constant, the actual numerical value for this one. Okay? Right, so that's the end of problem 23. Now we're going to go to number 32. Hi seniors, we're having fun and you're not. Haha. The next problem, number 32. I bet you're missing us right now. I know Daisy and Kinsley aren't missing you guys, so. So calculate KP. So what the heck? What you do when you get to this point is, just so you know, there's an equation. So if given Kc and you need to calculate Kp, there's a co-equation. You can go ahead and read about it if you want in your text, but it talks about how gases, we don't measure molarities of gases real well. We measure gases by doing what? Do you know? We read their pressures. So you know, like with the syringes, how they push against the walls of the syringe on the pressure sensor, that's how we measure concentrations of gases more easily. So that's why we have to do this conversion from concentration, which is, that's what the C stands for, to P, which is pressure. So we can set up these equilibrium equations like we've been doing, but we just have to convert it from the concentration to the pressure using this equation. So it's Kp equals Kc times. Do you guys remember RT from the ideal gas law?
0.082.
Okay, so Daisy still remembers R, and then the temperature has to be in Kelvin. You remember that? Okay, and then you raise that to the power of delta N of gas, where delta N of the gas is equal to the moles of product minus moles of reactant for gases only. Right? So these are the coefficients. You're probably like, where do you get these moles? Do you have to, do some fancy conversion? No, it's just the coefficients. So you just look at the coefficients. So then, for example, in A, the equation is H2 plus CO2 forms H2O plus carbon dioxide or monoxide. And these are all gases, right? Okay, you only do this with the gases. You only plug gases into this equation, this delta N here. Do you guys notice? Do you guys notice that? Well, you tell me. What do you think delta N is?
Well,
Let's look at the coefficients. Let's sort of make sure you see that.
delta N could be 1 mole of the product, right?
Okay, so all of this is products right here.
2 moles of product
Yep, so you have 2 mole of products.
equals or minus 2 moles of reactant.
That's right, because you have 2 moles of reactants here. So it's 2 products minus 2 reactants. So guess what? Delta N is 0. Yay. So what this tells us is Kp is going to equal Kc because, and I'll show the proof here, if you plug in, you'll get Kp equals Kc, which they give you as 0.77. Now, you can write all the fancy 0.0821 liter atmospheres per Kelvin mole times, and it gives you the temperature as 1020 Kelvin. But what I'm going to tell you is that wasn't even necessary because all this stuff was raised to the 0 power. And we know mathematically that anything raised to the 0 power is equal to what? 1. So anything raised to the 0 power equals 1. All this gobbledygook here is actually equal to 1. So you have Kp equals 0.77 times 1, which just equals 0.77. And that's your answer. Nothing's ever hard. It's just once you have to get into it to solve, to unravel the mysteriousness of it all. So we're going to look at number 36 now. And 36 goes like this. You have to understand the comparison between Q and K. So we're going to set up our 3 different scenarios. So when Q is less than K, okay, that means these are when everything's at equilibrium already. This is saying that at any point in time Q before equilibrium, we're not approaching equilibrium yet. We need to get closer to equilibrium. So if you have a really small number, it means that, so for example, so your number is 1 over 100, let's just say. And you need to get closer to K. What has to form more, the products or the reactants? Remember, this is product over reactant, all of our expressions. So we need to form more product, and that's what the reaction's going to do. It's going to proceed to the right. Okay? If Q is already equal to K, that means we're already at equilibrium. If Q is greater than K, then you have to draw a little picture for yourself that, hey, you know what, we have a lot of product and very little reactant. What's the reaction going to do to try to go back to, a ratio of 1 where your Q and K are equal? You have to get more reactant. So which direction does the reaction go? Oh, left. That's right. So we're going to form more product here, and we're going to form more reactant here. Okay. And so sometimes they ask you questions regarding, hey, which direction is the reaction going to go, and you're going to have to really, use what we just discussed to answer that question. All right, so new problem number 36. So Kp, they give you a constant of 60.6. Then they ask you to find Qp. Now, do you remember the difference between K and Q? This is already at equilibrium, right? What they want you to do is plug into, solve for Qp the value, and then do this comparison with it to answer the question, which way is the reaction going to go? So what I do is I take the equation, and I'm not going to write out the actual chemical equation, but I'm going to write the expression for it because I'm hoping by now you can see how I got the expression from the equation. So let me get a sort of head nod or something to indicate whether you get how I got this expression. Yeah? Okay. You guys are quick learners. You hear that, seniors? The sophomores are quick. All right, so then did you see where they said each of these concentrations is 0.10 molar? Okay, so I'm just going to go ahead and label all of these as 0.1 molar. And so now what you're going to do is you're going to reduce that down to 0.10 squared for the numerator. I'm sorry, cubed, right? See, because this first one is squared, correct? And you multiply by it again. You now are multiplying 0.1 by itself 3 times, aren't you? So that's cubed, and then on the bottom you're going to get 0.10 squared. Now this chemistry math is crazy like this. If you actually see it to set it up right, there isn't a whole lot of math. In other words, if you have cubed over squared, what are you left with? Yeah, so what does this simplify to? Without calculating it, this is like 3 minus 2. See, this is like 0.1 multiplied by itself 3 times.
So just point time.
Yeah. Do you see it? Do you see it, or do you need me to work it out?
No, I got it.
Okay, cool. All right, so that's it. And so now all you have to do is compare Q to K. So which direction do you guys are, Q is less than K. See it? This is less than that. So which direction are we going to go to have to sort of establish an equilibrium of 1? Okay. So we have, what do we have here? We have a lot.
You have to go right.
Yeah, because this means we have not very much product.
No.
Correct?
Oh yeah, I've seen that. Yeah.
And we need to get to equilibrium, which is 60. Okay, so we're going to form more product. Okay, so the answer is we're going to need to form more product because this is happening right here when we do the comparison. Fair? All right, so that's a tricky one. I get caught up on, I got to think about that to do that problem. So, all right. 42 is like easy. What are your thoughts on 42?
It's so hard. I'm just gonna have you ready.
Okay. So look at 42 and tell me your thoughts.
42. Yeah, she's annoying. I should just see if it's negative. Can't you just do like reaction to the problem?
Oh yeah. So now we're getting into some actual calculations of K. And this one's a direct sub-in, so this is an easy one. So then I'm going to show you the harder one, which is not that hard. It's really cool. Or I think it's really cool. So you guys can tell me how to set it up, and I'll just do it up here for the senior bunch. Or you can come up here and talk into this and teach the seniors. We can also do a picture-in-picture so they can see you.
Yeah. Look at me literally. So, okay, so could we just do N2, 0.114 molarity.
Okay, let's set up the expression first. So you said products over reactants like this? Okay, and you know the coefficients become the power. So you're comfortable with this? Yay. All right, now we're going to do the direct substitution.
Okay, so it's 0.114 molarity multiplied by 0.342. Do you put compared?
Yes, excellent.
And then divided by 0.0225. Why did you put that one to the start? Because it's a coefficient. Oh, just kidding. You just keep the coefficients with it.
Yes. So all you're doing is taking the molarities and plugging them in, and you don't even, the lovely part of this is you don't have to worry about the units this time. This time around you don't have to, for K's and Q's, you don't worry about units. Yay. And I'm just going to keep it to 3 sig figs because this whole thing's been 3 sig figs.
Alright, can I sit somewhere else?
Why?
I don't like it. Is it molarity?
No, no units. We don't do units with K's and Q's.
I forgot.
Seniors, what I do? Kenzie and Daisy are fighting.
Get.
Should I send them out? I should write them out. Okay. Uh-oh, things are falling. Right, so. So now we're going to do the harder part of this. This is going to be part 2 of finding actual numerical values for equilibrium. So we're on number 44, and the first thing to do is to balance the equation. So you have H2 and F2 equals hydrogen fluoride, and you balance it. What's the balanced equation?
1, 1, 1. I'm just kidding. I was 1, 1, 2.
Yay.
Yep.
Okay.
Loser.
Right.
I'm already up there.
This time I want you to set up a table off to the left here, and you want plenty of room. Do ICE. ICE. So the I stands for initial, and the C stands for change, and the E stands for equilibrium. Yay. And the next thing they do is they give you some values. So can you tell me what the initial concentrations of hydrogen?
I'll tell you.
Oh.
0.10.
Okay. So this is in moles. Recall that we need molarities. And the initial concentration of fluorine is?
0.05. 0.
And finally, we need molarities. So what do we divide each of these by to get molarities or concentrations? Molarity is equal to moles over.
Here, so 0.50. 0.0. No, 0.50. Yeah.
And then you do the math and tell me what the molarity is.
I don't even want to do the math. 0.2 for the first one, and 1. It's 0.10, not 1. It's 0.2. The second one is 0.10. But it's 0.2 on my calculator.
Still with me?
Yeah.
And then, did they give you any product yet? In the beginning?
Yeah, 2.
Well, this is the balanced equation, this is the recipe, but what did they initially mix together to react? Just these two?
Hydrogen fluoride.
They don't give you any of this stuff yet, though. What I'm saying is they don't give you a concentration of it yet, because it hasn't been made yet. So we're going to put a big fat 0 here, okay? What do you think is going to happen? Just like kind of make a mini prediction of if you mix two chemicals together, what do you think is going to happen over time?
Try to react, and it's going to change the ones that can do it.
So are we going to lose some of this or make more of this? And are we going to start making this, or what's going to happen?
We're going to make more of the F2 and we're going to start making some F or HF.
Okay, we can't really make more F2 from this. We can react these two, kind of like your tank on the left, you know, your aquarium. So right now we have a lot of water in the reactant, a lot of aquarium on the left aquarium, a lot of water, and no water in the right aquarium, the right tank. Make sense?
So then you're going to add them, and then they're going to turn into HF, and then it's going to equal out.
So would you predict that we're going to make this, so we're going to put a plus sign over here, and we're going to lose some of this?
Yeah.
Okay. Here's the fun part. Do you see these coefficients right here, 1, 1, 2? Mm-hmm. All right, we're going to make an algebraic, we're going to put in an algebraic variable here. And to represent the loss of a certain amount, we're going to put x in. And then over here, I'm going to put an x here also. That's going to represent the amount of molarity lost as they react. Okay. Then for every 1 mole that's lost, for each of these, 2 moles forms because of this coefficient. I'm just matching the coefficients up now. I just went 1, 1, and then 2. So this is going to be plus 2x. So then in the end, what we're going to have is 0.20 minus x, 0.10 minus x, and 2x. Does that make sense?
Yes.
So I just introduced the concept of making the ice chart. Okay.
That's all you do?
Ta-da! But now the next problem, 48, has you actually solve for it, and that gets a little... Okay?
That whole page is 48?
Yep.
Oh.
And then I think I'm going to stop there. So you guys ready to crank through this last one, and then we're done?
Yes, we are. What else are we doing?
Oh, well, you guys can work on problems. Go water your plants. That has to be done.
Yeah.
Okay. We're flying through this pretty fast because the seniors aren't here.
Oh, yeah. We don't like them. We should just keep it.
Am I going too fast? Seriously.
No. Perfect.
Alright, so the next step. We have, let me just give you a big picture here. You need to find Kc, right? So you need an expression. So if you look at your balanced equation, so your equation kind of looks like this. Okay. Yeah, I guess I'll just balance it for you, so because it's not like it's hard. So it's this, double arrow, because we're doing equilibrium, that means it goes in both directions. Alright, so you guys, I want to highlight the ratios, 2, 2, 1. You see that?
Yeah.
Alright, so it's really easy to write the equilibrium expression because now you have, alright, I'm taking the products, raising it to the power of, that comes from the coefficient. S2 is to the first power, so we don't have a because we don't have a coefficient, or we have a coefficient of 1. And then finally, in the denominator, we write the reactant to the second power. Now, this problem asks you to solve for the equilibrium concentration of H2, the actual value. This is what they're looking for. And in good old chemistry style, you know what Ms. Irwin always says, write down what you know, and then write down what you're going to solve for. And so this is your bullseye here. You're trying to find this numerical value. So what do? When you're trying to find a number value, you have to first, and all you know is your starting ingredients, you have to set up what kind of chart?
Ice chart.
Yes. You're on to me. So you set up your ice chart, and what do you guys think the molarity is, or what do they give you as initial info? They've got to give you something.
There's 0.45 moles of H2S.
Okay.
And then the liter 100 C, which is Celsius plus 270.
So the temp doesn't matter in this problem. The only time you're going to need the temp is in that KC-KP conversion. So they give you a temp just to tell you that you're solving for a constant value at a given temp, because the temp does change the constant value. All right, but we're not going to need it for this problem. Keep going. That's all it tells you. Great. So what do these brackets mean? No, the brackets means molarity. So what do we have to change this into? 0.15 molar. Good. And then we don't have any other initial stuff, which means they just threw some reactant in the tank. Kind of like the aquarium's full on the left, nothing on the right. So what do you predict is going to happen? What's the change going to look like?
Oh man.
Oh man.
What?
Oh, I can't take it.
You guys feel bad.
Oh yeah. Yeah, we'll leave. Yeah, we'll leave. We don't have to be here anyways. We already have our credits.
In here.
Oh my god. Not awkward.
Is it easy?
Yeah. So this pencil made me for wooden sharpness.
So I'm going to go ahead and finish this one, and I'll come back to conversations in a minute because we're recording. All right, so change is going to happen. This is like, okay, those of you just stepping in. So an equilibrium expression is products. So here's the balanced equation. And the equilibrium expression is products over reactants, and the coefficients become the powers. And the goal in number 48 is to solve for the concentration, the actual molarity of this hydrogen at equilibrium. So what we do is we set up something new called the ice chart. And what it does is it gives us initial materials, molarities before equilibrium, and then the change that occurs over time before equilibrium is established, and then that gives us the equilibrium values to plug into here to find H. Okay, so over time, this is like the aquarium on the left that it's full of water right now. The aquarium on the right has nothing in it yet. So what do you guys think is going to happen? This is going to move. So when this moves to the right, is this concentration going to go up or go down? Down. So we're going to put minus here. We're going to put minus 2x because you see that 2 right there? Okay? Because this is going to move according to this ratio. Okay?
Hey.
So it's kind of like as 2 molecules of this breaks down, 2 molecules of this forms, and 1 molecule of this forms. Get it? That's the reason for the 2 here. So we're going to lose 2x. The x is what we're trying to find. We don't know what it is. So as we lose 2 molecules of this, we're going to form 2 molecules of this, so it's plus 2. And we're going to form 1 molecule of this, so it's going to be plus x. All right, so then in the equilibrium, we're just going to put 0.15 minus 2x, and this is going to be 2x, and this is going to be x. Do you get it so far? Okay.
Yeah.
All right. And then what's going to happen is we're going to plug that back into the equation and solve for H2. So Kc, they must have given us Kc though. Did they give us this number? They had to. We don't need the temp.
Hydrogen sulfide according to the following reaction. 9.30 times 10 to the negative 8.
This number equals 9 point what?
9.30 times 10 to the negative 8.
Nice. Alright, so now we're going to have to substitute back in. So substituting back in and solving for H2. What you're going to do, I'm just going to come back up here and substitute in. So it's going to be, H2 is going to be, do you see it right there, 2x? Right? So we're going to do 2x squared times, do you see the x here represents s squared? X over. Okay, and then do you see this right here? That goes, that's H2S. See, track it, and we'll stick it right here. You see what I did? Okay, now what I'm going to do is I'm going to erase this. Wait a minute. Is anybody copying this? I'm going to erase this. Let's see. For a minute, just to show you what's the next step. So the next step is 9.30 times 10 to the negative 8 equals, I'm just simplifying, so I have 2x squared is 4x squared, so this is 4x squared times another x, so that's 4x cubed. The denominator, what we're going to do to keep life simple, chemists love to do this, is we're going to approximate this to be close to 0, okay? Because when you lose in equilibrium reactions like this, when you lose stuff, it's usually less than 5% of the original initial material. So I did a test already. It's less than 5%, so it's going to work. You have to test it. But so for right now, we're going to let this equal 0 for right now, just the denominator. You might say, well, why don't you make this 0? Well, because if I do that, then I lose the whole problem. I don't have anything to plug into to solve. So we're going to go ahead and assume that less than 5% of this original concentration is actually reacting. Then we can actually bypass the quadratic equation. Yeah. Alright, so to make a long story short, without spending time to work out all the math there, I did this in advance and I got x equals, or do you want to see all the steps? You want to see the steps? Because there's quite a bit of stuff that happens here. I do 0.15 squared times 9, so I'm just rearranging now, equals 4x cubed. Then I divided both sides by 4, so then I get x cubed equals 5.23 times 10 to the negative 10, and then I take the cube root of that. Okay, there's a math button on your calculator where if you press that, there's a symbol that looks like that, and so then you press that first and then you plug in your 5.23. okay, so you take the cube root of this, and that gives you 8.06 times 10 to the negative 4. A little bit of lag going on here. And then your last step here is H2, right? If you go back up to your ice chart, it's equal to 2x. Oh, and by the way, this is x right here. This right here is x. So 2x, so it's just 16.12 times 10 to the negative 4, which takes you down to, with sig figs, end of story, you're done. But you have to do a 5% check on the x, which means this value, I checked it to see that it was in fact under 5% of 0.15. And that's how I know I can approximate. So there's your answer right there, and I've pretty much just now gone over everything there needs to be gone over for you to be successful with this set of problems. I'm stopping.